morning, everyone. My name is Alicia. We're on the 31st of December 2012, and you're watching Science TV. Today we're going to explore one of the fascinating projects undertaken at CERN, the European Organization for Nuclear Research, located in Geneva. These projects aim at resolving some questions which the standard model of particles and forces does not describe. One of the experiments led at CERN and which we'll look into is ALICE, a large ion collider experiment, which aims at resolving some mysteries of the strong interaction. So first of all, we're going to talk about the theory of ALICE, including the aim and the functioning of the experiment, and then we're going to talk about the results and the future of ALICE. In ALICE, physicists aim at observing a quark-gluon plasma, that is to say, at recreating the conditions of the very young universe, which existed 10 to the minus 10 seconds after the Big Bang. Protons and neutrons were not formed. This belief that quarks and gluons are not confined at very high temperatures and densities, like in the young universe, is called the quantum chromodynamics theory. In undertaking this experiment, physicists hope to better understand the properties of the strong interaction, which would explain the mechanism of confinement of quarks and the generation of 99% of the mass of the nuclei. In order to recreate the conditions of the Big Bang, physicists need to reach very high energies by colliding two particles traveling at the speed of light. In ALICE, they accelerate two ions of plumb, which travel at the speed of light in opposite directions in the LHC, the Large Hadron Collider. This Hadron Collider of 27 km circumference belongs to CERN and is made of plenty of electromagnets, which generate a huge magnetic field of 8.3 Tesla and which experience an electric current of 1200 ampere. The very powerful magnetic field enables to lead the two particles in extremely precise paths, and the electric field enables to accelerate the particles according to the equation E equals Q times U. The process of ions acceleration has three main steps. First of all, a linear accelerator, called LINAC 3, accelerates plumb atoms from a pure material of 500 kilograms. The atoms progressively lose all their electrons and end up as nuclei after having been accelerated in the layer, the PS and the SPS. Then, two nuclei are sent in the LHC, which accelerates them until they reach the speed of light. Finally, they collide at a specific time in the ALICE magnet, in which the collision is recorded. In the summers of 2010 and 2012, physicists involved with ALICE announced the observation of a quark-gluon plasma, marking the success of ALICE.
I'm standing in front of the very famous Science Museum of Paris called Palace of Discoveries, and I'm about to interview one particle physicist who's going to clarify some more points about the ALICE experiment. Follow me. So here I am. I'm interviewing the particle physicist Julien Babel, who has already worked at CERN a few years ago. So my first question would be, why do you need to study the plasma quark-gluon to be able to say if this plasma interaction, like quark-gluon, represents 99% of the mass of the proton?
Because you have access to a very big energy, so the quark and gluon are not linked like in the proton, so it's easier to study them because there is less interaction between them, and so you have every quark is not linked to the other like in the proton, so you have a very big space with a lot of particles, and you can see what are the interaction, the power.
And also, how long do you think it's going to take to study all the properties of this plasma?
Yeah, for the moment, the energy is just 2 times lower than the max, the machine, the LHC, and maybe in 3 years.
In 3 years.
The max power will be reached.
Okay.
And we need some more statistics too. We have to accumulate data every year to have a big amount of data to study.
Approximately 5 years?
Yeah, 5 years, I think.
5 years?
To study in details the plasma.
Thank you very much.
No problem.
So, the results of Alice have already validated the quantum chromodynamics theory, that is to say, that at very high temperatures and densities, quarks are no longer confined in the nuclei, but exist in a quark gluon plasma. But some further research needs to be done in order to determine if the strong interaction represents 99% of the mass of the nuclei. We'll look into it in the future. But in any case, thank you for watching Science TV.